Hello, let's continue working on some equilibrium problems. So this one says that the K for the reaction between hydrogen iodine to form hydrogen iodide is 55.17. It says if you place 1 mole of each of hydrogen and iodine in a half-liter flask at 699 Kelvin, what are the equilibrium concentrations of all your species, the H2, I2, and the HI? So since it's an equilibrium problem, we're going to start with the K EQ expression. So KEQ is equal to the concentration of HI squared divided by the concentration of H2 times the concentration of I2. We are given that the equilibrium constant, the KEQ, is 55.17, and we're trying to find all the other concentrations. So in this case, since we don't know any of the concentrations at equilibrium, we are given some form of concentration here. It's 1 mole of the hydrogen and the iodine in half a liter, but that's initially. That's not at equilibrium, and so that means we need to make an ice chart. So let's do that. So I have H2 plus I2 yields 2HI, and ice, so initial. So for the initial concentration, it tells us that we have 1 mole divided by 0.5 liters. So let's see. Concentration initially of the H2, 1 mole divided by 0.5 liters. So that's going to be 2.0 molar. And that's the same for the I2 initially as well. So for the ice chart, initially this is 2 molar, and this is also 2.0 molar, and initially we don't have any product yet, so that's 0 molar. Some of the H2 is going to get used up, and some of the I2 is going to get used up. So let's say that the amount that they get used up is X, and so we're going to remove an X amount from H2, and it's going to be the same amount from I2 because it's a 1-to-1 ratio. For the products, we're going to form 2X because it's a 1-to-2 ratio, so plus 2X. So then at equilibrium, this is 2 minus X, 2 minus X, and then this is 2X. So let's plug these in back into our equilibrium expression. So our KQ is 55.17. Our HI concentration is 2X. So that's 2X all squared. So that's really 4X squared. Divided by 2 minus X times 2 minus X. I'm going to give you a minute to go ahead and plug it into your calculator to solve for X here. And if you're still struggling figuring out how to get those values from your calculator, make sure that you get some help from one of your friends or from your math teacher. If you are somebody who is pretty good at this and figuring out different ways to do it, or really good with the window and adjusting it, please help others. A lot of people struggle with using their calculator to find X here. Okay, so hopefully you plugged it in. I got that X is equal to 1.58, and this is a concentration, so molarity, molar. And so my question was asking for the equilibrium concentration for all species. So concentration for HI at equilibrium is 2x. So 2 times 1.58 is 3.16 molar. Concentration of H2 is the same as the concentration of I2 at equilibrium. They are both right here, 2 minus x. So 2 minus 1.58 molar. And so that gives you 0.42 molar. So that's a 4 there. All right, let's move on to the next one. So the next one says, in the previous question, so we're still talking about H2 and I2 forming HI. Suppose that the initial concentration of H2 is 1 molar and the initial concentration of I2 is 3 molar. So they are different concentrations. What are the equilibrium concentrations of, again, all species? So it's exactly the same question as the previous one, except right here your initial concentrations are different. One of them is 3 molar and the other one is 1 molar as opposed to both of them being 2 molar. So we're going to do the same exact thing, just with a different ice chart. So here, my ice chart, let's see, we have H2 plus I2 yields 2HI. Alright, ice. So the initial concentration for the H2, they tell us, is 1.0 molar this time. The initial concentration for I2 is 3.0 molar. And again, the HI is a product, it has not formed yet, so initially it's 0 molar. The change in this case is still the same. We're going to use a certain amount of of H2, we'll call it X. Because this is a 1-to-1 ratio, we're going to use the same amount of I2 to react with the H2, so minus X, and we're going to form 2X in terms of HI because it's a 2-to-1 ratio still. The equilibrium, this is going to be 1 minus X, this is going to be 3 minus X, and this is going to be 2X. So then our KQ expression, 55.17, is equal to the HI concentration, so 2x squared, divided by the H2 concentration is 1 minus x, times the I2 concentration is 3 minus x this time. And again, I'll give you a minute to plug it into your calculator and solve for x. And please help each other figuring this out on the calculator. A lot of times if you're having trouble, if it gives you an error, that means your window is not adjusted. So what I do is I don't adjust my window, I just try it first, and then if it gives me an error, then I go back and look at my window and see if I can figure it out. For this one, when I plugged it in, I got that X is equal to 0.97 molar. Okay, so now to figure out all your concentrations, let's start with H2. So H2 at equilibrium is equal to 1 minus X, so 1 minus 0.97, and so that's 0.03 molar. For I2, that's 3 minus X, so 3 minus 0.97, so that's 2.03 molar. And then the concentration of HI at equilibrium is 2x, so 2 times 0.97, and so that's equal to 1.9 molar. Let's try the next problem. It says I have 100 milliliters of 0.02 molar lead nitrate. It's mixed with 150 milliliters of 10th molar sodium chloride. And it's asking, will a precipitate form? And they give us the KSP for PbCl2. So let's look at what's happening here. So I have two solutions. So I have 100 mils of 0.02 molar of the lead nitrate, and I have another solution that's 150 mils of 10th molar NaCl, and I'm going to mix them together. Now, if I mix those two together, lead nitrate and NaCl, if a precipitate forms, what precipitate would that be? So if I mix those two together, one of the products would be NaNO3, sodium nitrate. That's very soluble. That would never precipitate according to the solubility rules. Remember, you need to know that one rule. The other one is PbCl2, which actually is slightly soluble, or, in other words, insoluble. Now, if you didn't know that, they kind of told you the KSP for PbCl2 is 1.4 times 10 to the negative 8, so that's a pretty small number. Remember, K, whether it's KQ or KSB or KC, those Ks, the equilibrium constants, tell you whether a reaction is product favored or reactant favored. So this is a very, very small number. This is 0.000000014. So it's a very small number that tells you it's very reactant favored. So that means not very many of these are going to dissociate or dissolve. And so that tells you this would be the precipitate if there was a precipitate to form. So the KSP is for salt, an ionic salt, dissociating. So let's write down that process. So PbCl2 solid dissociates into Pb2 plus ions and 2Cl minus ions. The KSP, the expression for this, would be the concentration of Pb2 plus times the concentration of the Cl minus. Don't forget to square it. And then you do not include this. You don't divide by this because that's a solid. You don't include it. You only include the aqueous ions or if you have gases. So that's my expression. And they tell us that that number is 1.4 times 10 to the negative 8th. Okay, so then how does this help me? So when I mix these two together, I can figure out what the concentration of Pb2 plus is and the concentration of Cl minus is, and I can calculate the concentration right now, which would be Q. And I can compare that to this number, so I can compare Q to K, because this is when it's going to start precipitating. So I can compare Q, which is my reaction quotient, this expression right now, versus when it's at equilibrium, and find out if I'm at equilibrium, so it's going to start precipitating, or if I'm before that, or if I'm after that and it's already precipitated. So let's do that together. So we're going to find Q. So Q is the concentration of Pb2 plus times, that's a 2 plus there, times the concentration of the Cl minus squared. Now what is the difference between this expression and this expression? Because they look pretty similar, right? This is right now. This is specifically at equilibrium. So for Q, I can plug in my concentrations right now, whatever they are when they're mixed. This only applies when we're at equilibrium, and we're talking about equilibrium for a solution. That means when it's fully saturated. So any extra, it's going to precipitate. It's about to precipitate when you're at equilibrium. That's what equilibrium means for making a solution. So right now, I'm going to plug in the values for the Pb2 plus and the Cl minus concentrations. Now, it's not these concentrations. Why not? Because when I mix them, the volume changes. And so I have to figure out, when you mix these two solutions together, what is the concentration of the Cl minus and what is the concentration of the Pb2 plus. So let me do that on the side. So let's start with the Pb2 plus. So the Pb2 plus concentration, I have 100 mils, so 0.100 liters, and it's 0.02 molar, so 0.02 moles per liter. That gives me the moles of Pb2 plus, and then I divide by the total volume. The total volume is 100 mils and 150 mils, so that's 250 mils, which is 0.25 liters. So the concentration of the Pb2 plus when you mix the two solutions is 0.008 molar. Let's do the Cl minus in the same way. So I have 150 mils, so that's 0.15 liters. It's 10th molar, so 0.10 moles per liter. Multiply those together, you get moles, and then divide by the total volume, 0.25 liters. And so the concentration of the Cl minus is 0.060 molar Cl minus. So these are the concentrations of the Cl minus and the Pb2 plus when you mix the two solutions together. So I'm going to plug these in into my Q expression. So 0.008 molar times 0.060 molar squared. So Q ends up being 2.88. I'm not really looking at sig figs here, because we're just trying to figure out if a precipitate forms or not. Times 10 to the negative fifth. And that's my Q. So now what does that mean? Well, if when you multiply these two together, the Pb2 plus times the Cl minus squared, if you get this value, then you're at equilibrium. So that's when it starts precipitating. So what you do is you compare Q to this value. You compare Q with KSP. So in this case, is Q equal to, greater than, or less than KSP? So in this case, it's much larger than the KSP. Remember that KSP is products over reactants. And so right now my Q is way larger, right? What does that mean? That means my products are way larger than they would be at equilibrium. And so that means that a precipitate will form. If your Q is lower than your KSP, that means these concentrations of my ions is very, very little. Not very much has dissolved. So very little of this is there, and so it's not going to form your solid. If Q is much larger, that means I have way too much of these than I could at a saturated solution, so that means the extra will precipitate. So in this case, a precipitate will form. Let's shift gears to Le Chatelier's principle. This is one of those topics where people either love it and they think it's very easy, or they hate it and they think it's really complicated. Let's first define what Le Chatelier's principle says. And so Le Chatelier's principle says that when a system at equilibrium is subjected to a stress, the system will shift in the direction that minimizes the effect of the stress. Will shift in the direction that minimizes the effect of the stress. Now, what does stress mean? Stress means you've changed your conditions. And so you could have changed the concentrations. You could add more reactants or products, or remove some of them. You could change the temperature, you could change the volume, or you could change the pressure. So we're going to look at each of these changes and how they affect the equilibrium position. So let's look at this reaction here. We have nitrogen reacting with hydrogen gases to form ammonia gas. And they give us the delta H. They say it's negative 92 kilojoules, so that's an exothermic reaction. That's going to be important when we start talking about temperature or heat. So let's start with changes in concentration. So right now, you're at equilibrium. That means that your forward rate and the reverse rate are equal to each other. You're at a given temperature, and so your K, or KEQ, is a certain amount. Remember that K is products over reactants. If you change conditions, unless it's temperature, the reaction will shift in a way to minimize that stress, and it will reach a new equilibrium position where K does not change, where K remains the same. So let's look at if you add more nitrogen. So you're adding more of this. So you've reached equilibrium and you're happy, but now you're adding more reactants. Now there's too many reactants. That's not good. And so it's going to shift to one of the sides to get rid of that extra nitrogen, or to use up that extra nitrogen. So which way would that shift? That would shift to the right to make more ammonia so that you use up that extra nitrogen. So reacts to use up the excess nitrogen, and so shifts right. Now what does that mean, that it shifts to the right? Remember that at equilibrium, the forward rate and the reverse rate are equal to each other. When it shifts right, what that means is the equilibrium is disturbed, so the rates are no longer equal to each other. When it shifts to the right, that means that the forward rate is actually faster than the reverse rate for a little while until it compensates, and then it goes back to equilibrium to reestablish equilibrium where the rates are equal again. All right, let's look at the next one. If you add more hydrogen, so same idea here. You're at equilibrium, everything is great, but then you disturb it by adding more of the hydrogen. So the system wants to get rid of that extra hydrogen. You have too much hydrogen. And so to get rid of the hydrogen, it's going to, again, shift to the right to use it up. And so this one will also shift right. Okay, let's say you're adding more ammonia. So now I'm at equilibrium and I'm going to disturb it by adding more of my products. I have too many products. So which way would it shift to use it up, to get rid of it, that extra? It's going to shift to the left. So that you can use up your ammonia, your extra ammonia. All right, how about if you add argon? And it tells you it's inert, it's a noble gas, doesn't really do anything. Is it going to affect your equilibrium? No, no change will happen. Has no effect whatsoever. When would it have a change? If your volume changes because of it. So if when you add more gas, the volume increases, then there would be an effect. But if it's a rigid container where you're just adding extra gas, nothing will happen. It's not going to affect anything. All right, now let's look at changes in pressure. Now, changes in pressure will only affect the equilibrium position if it's due to a change in volume. So if your pressure changes because your volume changes, then it's going to affect the equilibrium position. So this is only if due to volume change. All right. If you were to increase the pressure, it will always favor the side with less gas particles. Favors side with less gas particles. Let's think about this for a second. Pressure is collisions of gas particles, right? So if you increase the pressure, that means you have too many collisions. And so to get rid of those extra collisions, it wants to go to the side with less gas particles, so it'd have less collisions. With the same way, if you decrease the pressure, then it's going to favor the side with more gas particles. Again, that should make sense because if you decrease pressure, that means you have less collisions than you should. And so to make up for that, it's going to go to the side with more gas particles so that there are more collisions. So in our reaction here, let's look at it. So if you increase the pressure, it's going to go to the side with less gas particles. Right here in the reactants, you have 4 total gas particles. In the products, you have 2. And so in this case, it's shifting right. If you decrease the pressure, then you're going to the side with more gas particles, so that would be left. Let's look at changes in volume next. And so when you change the volume, that affects the pressure, or it affects the concentration. You can think about it either way. If you're talking about gas particles, you can think of it in terms of pressure. If you are talking about aqueous solutions, then you can think about it in terms of concentration. And actually, you can think about it in terms of concentration either way, because even if it's gas particles, it will affect the concentration as well of the gas particles. So an increase in volume means that you are decreasing the concentration. If you have a certain amount of moles in a liter, so let's say you have a 1 molar solution, or your concentration of the gas particles is 1 molar. So 1 mole for every liter. Let's say you increase the volume, so now it's 2 liters. That makes it half molar, so it decreases the concentration. So let's write that down so that we have it here. So an increase in volume means decrease in concentration. So now my concentration is too low. So to make up for it, we're going to go to the side that has more particles so that my concentration goes back up. So favors side with more particles. If you decrease the volume, you make the volume smaller, then your substances are more concentrated. You increase the concentration. So now your concentration is too high, so to make up for it, it's going to favor the side with less particles. And so if we look at our reaction up there, the side with more particles, that would be the left. The side with less gas particles, that would be the right. Okay, now let's look at temperature. So when you change the temperature, you have to decide or figure out whether your reaction is exothermic or endothermic. So with these, it depends on if reaction is exo or endo. And you treat the temperature, if you increase it or decrease it, as if you're adding or removing heat. So if you increase the temperature, that's as if you are adding heat. If you decrease the temperature, that's as if you are removing heat. And so you treat the heat as either a reactant or a product. So let's look at our reaction here. So my reaction, I have delta H is negative 92 kilojoules, so that means it's exothermic. So you think of heat as either a reactant or a product. If it's exothermic, that means you can view heat as a product. So heat is a product, and so if you add heat, that means you're adding a product. So to get rid of that product, you're going to shift to the left. If you are removing heat, then you're removing a product, so to make up for that, it's going to shift to the right. So let's write that down. So here you're adding heat. So in this case, adding product. So it would shift left. If you're removing heat, in this case, you're removing product. And so it's going to shift to the right. Obviously, if it's endothermic, then it would be the opposite. You'd be adding or removing a reactant as opposed to a product. Okay, let's practice some more. We have 2NO2 producing N2O4 plus heat. So this is another exothermic reaction here. We're going to decrease the volume. So which way would it shift? So if you decrease the volume, that's as if you're increasing the concentration. So shifts to side with less particles. So what side has less particles? That would be the right. Okay, let's look at pressure. And again, we're assuming this is pressure due to volume. So if you increase the pressure, it favors side with less gas particles. And so in this case, the one with less gas particles, that would also be the right. Okay, let's take a look at temperature. You decrease the temperature, so you are removing heat. In this case, heat is one of your products. So if you're removing a product, it's going to shift to the right to make more product. So all of them are going to the right. Let's look at the next reaction. We have 2H plus 2CrO4 minus yields Cr2O7 minus plus H2O. This one's a little bit trickier than the other ones. It's not as straightforward. So let's look at it here. The first thing, we're going to add HCl. Now, if we look at our reaction, there is no HCl. So at first glance, you think, well, then it's not going to change anything, but it will. Let's think about what HCl is. HCl is made up of H pluses and Cl minuses, right? So when you add HCl, that's really like you're adding H pluses and Cl minuses. We don't have any Cl minuses in the reaction, but we do have H plus. H plus is a reactant. So this is as if you're adding more H plus or more reactant, and so it's going to shift right. How about if we had NaOH? So again, there's no NaOH in our reaction, but NaOH is made up of Na pluses and OH minuses. Since this is a solution, so when you put it in the solution, it dissociates into Na plus and OH minus. And so there's no Na pluses, there's no OH minuses in the reaction. However, we know that OH minus is basic. And we know that the reaction has H pluses, which are acidic. Whenever you put H plus with OH minus, what happens? That's right, you form water. And so the OH minus actually removes the H pluses. And so really, it's like you're removing one of your reactants. And so you are at equilibrium. Now you have less reactants. So what are you going to do? It's going to shift to the left to make up for that, to make more reactants. So shifts left. Okay, how about NaCl? So if you add NaCl, that's really like adding Na pluses and Cl minuses. There's no Na pluses or Cl minuses in the reaction. There's nothing really that either Na plus or Cl minus would react with or combine with or anything like that. And so there would be no change in the equilibrium position here. Okay, how about water? If I add water, what would happen? Now, this one's a trick question. Some of you, there is water in the reaction. Some of you might say, well, there's water in the products. So if I'm adding a product, it would shift to the left. Now, that might be the correct side. It actually does shift to the left, but that is not the correct reason. Why can't I use that reason? Why can't I say it's because I'm adding a product, so it's going to shift to the left? The reason is because water is a liquid. It does not affect the equilibrium position. If you add a solid or a liquid, it does not affect the equilibrium position. Unless it dissociates or does something, like these. It does shift to the left, however, not because water is one of your products, but because when you add water, it affects the volume. If you add more water, then your volume increases. So if the volume increases, that means the concentration decreases, which means it will favor the side with more particles. And when we say favor side with more particles, we're talking about either gas particles or ions, not water, not liquids or solids. Those are not taken into consideration when you're talking about equilibrium. And so if you look at your reaction, we have 4 particles, 4 ions on the left. We have only 1 on the right, and so it's going to favor the left or shift left. And so you could have predicted the correct answer, but if it asked you to explain, then you would have lost the points on the explanation if you said that it's because water is one of your products. All right, last one here. How about if you heat the flask? Well, if you heat or cool something, it's going to depend on whether it's exo or endo. So let's, for fun, do both because it doesn't tell us here. So we'll say depends on exo or endo. So let's assume it's exo. If it was exothermic, that means heat is one of your products. And so if you add a product, it's going to shift to the left. If it's endo, that means that heat is one of your reactants. It's on this side, so if you add a reactant, it's going to shift to the right. Last bit of notes here looks at how the equilibrium constant, K or KEQ, is affected by different changes, or these stresses that we just talked about. So remember that the equilibrium constant is for a reversible reaction. So let's say that you have the reversible reaction A yields B. And so K is going to be the concentration of of B. Alright, so K is the concentration of B over the concentration of A raised to the power of their coefficients, of course. So products over reactants like we've always done. So let's say that I add a reactant or a product, or I remove a reactant or a product. Well, let's see. Let's say that I add A. So let's look at how that's going to affect K. So K is the concentration of B over the concentration of A. So let's say I add A, so this number will increase. Now, in my reaction, if I were to add more A, which way would it shift? It's going to shift to the right to make more B. So yes, I increased A, but I also increased B. And it happens that they increase by the same factor, and so K actually stays constant, remains the same. So there is no change. Let's say I add B. Okay, so K is concentration of B over concentration of A. So let's say I increased B, I added more B. If I added more B, which way would the equilibrium shift? It's going to shift to the left to make more A. So now my A also increases, so again K remains the same. What if I were to remove A? So K is the concentration of B over the concentration of A. So I decreased A. So what happens if I decrease A? Which way would it shift? It would shift to the left to make more A, or to use up B. So you can think of it as B also decreases, or A decreases and then increases again when you form more of it. So again, K remains the same. So no matter what you do to the concentration, K will have no change. It will remain constant when you add or remove reactants or products. Okay, let's look at a catalyst. So if you were to add a catalyst, what does a catalyst do? A catalyst speeds up the reaction. Speeds up reaction without getting consumed. That's the definition of a catalyst. So K, again, is the concentration of B over the concentration of A. If I make the reaction go faster, it's just going faster. It's not going to change the concentration of A. It's not going to change the concentration of B. So again, no change. So adding a catalyst does not change my value for K. The only thing that does affect the value of K is temperature. If I increase or decrease the temperature. So I'm going to actually change this wording a little bit. I want you to write change in temperature as opposed to increase in temperature. We're going to look at increasing and decreasing the temperature. Well, it depends on if it's exo or endothermic. So let's look at exo first. So A yields B. If it's exo, then heat is one of the products. Okay, so now let's say that I increase my temperature. Okay, we said that K is the concentration of B over the concentration of A. And let's say I increase the temperature. So in this reaction, if I were to increase the temperature, I'm adding more heat. Which way would it shift? It's going to shift to the left. So if it shifts to the left, then it makes more A. So my A increases. My B, you can think of it as remains the same, or if you're really accurate, if you're making more A, you're losing some B, and so that decreases. And so I shifted to the left without anything to balance it. So I made more A and used up B. And so now my K will decrease. Let's say I decrease the temperature, so I cool it down. If I cooled it down, then it's going to shift to the right to make more heat, and so it's making more B in this case, and so my K increases. Okay, now let's look at if it's endo. If it's endo, then A plus heat yields B. Again, K is the concentration of B. Over the concentration of A. All right, so let's say I increase my temperature in this case. If I increase the temperature in this reaction, which way would it shift? Well, if I'm adding more heat, it's going to shift to the right to make more B. So now my B increases. So that makes K higher. So K increases. If I decrease the temperature, that means in this reaction I'm removing heat, so it's going to shift to the left to make more A in this case. And so now this one, the denominator increases, and so K decreases. So the only thing that will affect the value for K is temperature. There's no change when you add or remove reactants or products. There's no change when you add a catalyst. The only thing that will affect it would be the temperature. All right, the next topic, which is in the following video, is going to be about equilibrium constant in terms of pressure in gaseous systems.